it's time for the next talk by Edoardo Persichetti from the Florida Atlantic University. And the talk will be about less FM, fine-tuning signatures from the code equivalence problem. So please, Edoardo.
Thanks, Guglielmo. First of all, thanks to the organizer for allowing me to present this work. I'm very happy to be able to share with you. This is a joint work with my colleagues Alessandro Barenghi from Politecnico di Milano, Jean-François Bias at University of South Florida, and Paolo Santini from Università Politecnica delle Marche. We presented this recently at PQ Crypto 2021, which is the flagship conference for post-quantum cryptography. So you'll see the tone of the work, of course, is going to be a lot more skewed towards the cryptography side. Here is a quick overview of the talk. It's not going to be very long, so I'm just going to briefly give the motivation for our work, and then talk about the code equivalence problem and introduce it briefly, and then describe the less protocol and the variants that compose the main part of this work, and then talk a little bit about performance and give some conclusions. Okay, so the motivation is usually very simple. This is the slide that I have for audiences that is not fully composed of cryptographers. Usually, if you are following the area, you are aware of the fact that most of the public key cryptography that we use nowadays is based on RSA or discrete logarithms of some sort, and a lot of these, especially the ones that are widely used, are going to be threatened by quantum algorithms like Shor's algorithm that allows to solve all these problems in polynomial time, or quantum polynomial time at least. And the community is raised awareness in recent years about this problem, and therefore certain initiatives have started. For example, NIST, which is the Institute for Standardization in the US, has launched a call for standardizing new public key cryptography standards that are secure against quantum algorithms. And there are several areas of research that are essentially trying to exploit different problems. And among these is code-based cryptography, yes, and is one of the main ones, in fact. So code-based cryptography utilizes methods from coding theory. And here I'm going to jump to the state of code-based cryptography at the moment, which is that, in fact, this represents one of the main players in the post-quantum context, second only to lattices, I would say. And in fact, we have a lot of great constructions for CAM and PKE, which are the technical steps to obtain key establishment functionalities. So something that we can imagine will take the place of both encryption schemes, but key exchange schemes as well. But unfortunately, we don't really have signatures at the same level of satisfaction that we have for CAMs and PKEs. And very, very broadly speaking, we have two traditional ways of constructing signatures. The first one is the hash and sign method that is based on trapdoors. And this traditionally leads to very large keys, which is kind of common to all of code-based cryptography, although it has small signatures. And it's also very slow signing process. Or we can use zero-knowledge proofs, essentially with identification-based protocols. And this tends to lead to instead very large signatures, although it does feature small keys. So either way, and again, this is a very, very broad overview. We have these problems in code-based cryptography that neither approach to date yields very satisfactory results. And all of these approaches in code-based cryptography are exploiting what code-based cryptography does, which is use the hardness of the coding. So in 2020, with Bias, Micheli, and Santini, we proposed a new protocol, which is called LESS, which stands for Linear Equivalence Signature Scheme. And it's because it's based on the idea of code equivalence instead of the hardness of the coding. And in this work, we essentially propose some protocol variants and new parameters and a variety of optimizations that are aimed, in fact, at getting better performance for the scheme. So without further ado, let me recap quickly what the code equivalence problem is. And I'll start a little bit behind because we're talking about code-based cryptography. And so we have to mention that the McEliece crypto system was pioneer in this sense, and it uses, of course, error correcting codes. I have to thank Relinde for her previous talk. She introduced a lot of notions of coding theories. Here, I can be quick about this. Of course, we consider here QRE codes, so subspace of dimension k of fq to the n. And the crypto system is based on the hardness of the coding, as I was already mentioning. And the key is that we're supposing that the adversary is faced with the problem of decoding a random linear code, which is known to be hard. And in fact, we have one version of this, which is the most popular one, I would say, which is the computational syndrome decoding problem, which essentially asks to decode this random code. Yes, here we have a parity check matrix H, which is random, a vector in the space and a fixed weight, and we're required to find a vector of that weight such that that equals the syndrome. So for this to happen, because the crypto system uses a trapdoor, of course, my public key needs to look like a random code. And this is why I had the slides to mention that essentially our chosen code should be unrecognizable so that we can leverage the hardness of SDP. And for this, a certain version, if you want, of the code equivalence problem already is present in the code-based cryptography literature, just not as a standalone problem, right? So what is this problem exactly? It's not going to be exactly what is used in the Mechalis crypto system, but it gives us a way to start. Essentially, we say it's a very well-known concept that two codes are permutationally equivalent. If there is a permutation that maps one into the other, that should be C prime, the second one. So essentially, every code of C prime, every code word of C prime is the permutation applied to the code words of C. And in fact, we can extend this notion using linear isometries, right? So we get what is called a linear code equivalence, which is the same, except that instead of using permutations, we use, in fact, linear isometries, which is nothing but a permutation with some non-zero scaling factors. Yes. There is an even more general notion that is that of semi-linear isometries, but we do not consider this here because, long story short, it doesn't really add anything to the security of what we are considering in terms of cryptography. So codes are equivalent if there exists a map, a permutation map or a linear map between them. And we can, in fact, describe these using generator matrices as well in a very convenient way. So clearly, two codes are equivalent by permutation if there is a left invertible matrix and a right permutation, so that G prime is equal to SGP. And the linear version uses instead a matrix Q, which is known as a monomial matrix. Yeah, so this is like a permutation matrix, but instead of having ones in each row and column, we have, again, non-zero scaling factors. So with this formulation, it's easy to describe what is called the code equivalence problem. What is interesting, in fact, is that we can see this as a group action of this group here on the set of generator matrices, which are the full rank matrices in FQ of dimension k times n. Yes, so the fact that this can be seen as a group action is kind of important for cryptography because we can use this in certain protocols that the previous ones could not use. So the code equivalence problem can be defined in the two flavors, permutation and linear, depending on what notion of code equivalence you're using, by just producing two generator matrices G and G prime for the two codes and determining whether the two codes are permutationally equivalent or not. So this is traditionally phrased as a decisional problem, although of course for cryptography we are interested more in the computational version of it. So essentially finding a matrix S and a matrix P or Q that link the two codes. Right, so this problem it's well known in coding theory, as I said, connected to the well-known notion of code equivalence, and has been studied for a very long time. And in fact, Petrank and Roth proved that this problem is probably not NP-complete unless the whole polynomial hierarchy collapses. But on the other hand, we have existing algorithms like we have for every problem that we use in cryptography, right, for factoring, etc. And these algorithms are efficient in certain particular cases, corresponding to the codes having certain properties. I do not have really the time here of doing an overview of the attacks, but what is to be kept in mind is that the complexity of all the different techniques is essentially exponential, and it's relatively easy to find intractable instances. For example, one could take weakly self-dual codes or codes with a large hull, or other particular types of codes. And in general, for the case of random codes, the complexity is high. So this is a good problem to use in cryptography. It is, again, unlikely to be NP complete, but this is not really a requirement. So we would like to use this to build a protocol itself. And this is where LESS comes in. So LESS is a zero knowledge identification scheme. So it's going to feed into like the second type of constructing signature schemes. And this is a one slide summary of LESS. It's a very intuitive protocol. It follows, as I was saying before, what one can generally do with group actions. Yes. So here we have a linear code that we fix, and then we select a transformation, which is going to be exactly our group element, and we produce an instance of the group action, yes, for our public key. So G prime is SGQ technically, although in practice we can really choose this to be the systematic form, is a more convenient choice. And then what the prover does to do the computation to prove himself to the verifier is he will choose a second instance of the same group action, right, with a different element. So he will choose a Q tilde, and then we produce a systematic form of GQ tilde. So this is the same as above. We said that we can use the systematic form. We might just as well use the systematic form. And then commits to this value by hashing it and sending the hash value of G tilde. Yes. So we now have a code G that we start from that is known. We produce a public key G prime. We produce this kind of ephemeral instance G tilde. We send it to the verifier. The verifier will ask us a challenge, right? This is a bit 0 or 1. And then we respond with either Q tilde or Q inverse Q tilde. So the Q tilde obviously ties to the ephemeral instance, so we can verify this, right, by using G times Q tilde, yes. And if we respond with the other one, this is where the secret key is contained. So this allows us to verify using the public key, yes, because the Q inverse undoes the Q here, and then we can verify the hash value just as well. So it's a very simple, intuitive protocol. It's easy to see that the soundness error, so the probability of cheating on an adversary is 1/2, because an adversary can always try to produce an answer that verifies in either the case 0 or case 1. What he cannot do is answer both challenges simultaneously, right? So we have a 1/2 soundness error, or cheating probability, as you want to call it. And this means that essentially we repeat the protocol a bunch of rounds, T rounds, and this gives us the error that we desire. For example, for T equal 128, we get a high level of authentication, T to the 2 to the minus 128, which is desirable, right? And this is the reason, by the way, why these kind of zero knowledge protocols lead to very large signatures that we have to repeat several times. And then the protocol can be converted by standard means, for example, the Fiat-Shamir transformation, which makes it non-interactive. And then this also gives us a proof of security for EUF CMA, which is the existential unforgeability property. So what can we do to improve this protocol? First of all, here notice that we have two different types of responses, B equals 0 and B equal 1. And the B equals 0 is this purely random matrix Q tilde, right? So we'll see what we can do here. But essentially, here we're going to present already the multiple repetition version converted to a signature. The key generation is going to be the same. And for commodity, I will just call G0 the initial public matrix and Q0 the identity matrix. And then the rest is the same here. And when I sign, again, I'm choosing a bunch of different matrices, Q tilde, J, where J is one of the T rounds, right? So for each round, I will produce my G tilde and then hash them all together with the message. This is what Fiat-Shamir does. But the hash of this, so this commitment, here, instead of producing like a uniform random bit string, we'll have a weight restricted hash function so that the probability of having a 0 is not exactly the same as the one of having a 1. Right, so then we parse our challenge vector, we get bits like before, and then for each bit we answer with this is a compact notation. So essentially saying if hj is 0, we just answer with Q tilde itself. If hj is 1, we answer with the public key using the secret key here. Okay, so it's like a compact notation, and then we verify basically each round, right, by checking the corresponding matrix and then putting them all in a hash and checking the hash. This is, again, what the Fiat-Shamir does. What is to notice here is that what I mentioned is that we have this weight restricted hash function. What's the reason for this? So basically, we're going to try to have a lot more zeros than 1 here. And in fact, this is not a new idea. Fiat and Shamir in their original work already were hinting at something like this. It doesn't change the security proof. All we need to do is modify the forking lemma to change the output distribution. In fact, the challenge set will have to go from 0, 1 to the t, which is the uniform one, to the set of fixed weight strings. Yes, so it's enough for us to choose more rounds. So this seems counterintuitive. We're going to have more rounds, right? So instead of choosing t equal to lambda, the security parameter, which is going to choose a larger value. But the advantage is that the 0 bits correspond to a purely random matrix, as I was mentioning before. And so we can instead just use a seed, a short seed for a pseudo-random number generator. And this will be a lot shorter than sending an entire matrix, of course. So we can considerably reduce the signature size because in the context of the number of rounds that we have, only few of them, I will actually send an entire matrix, which is the case q inverse q tilde. But for the rest of, I will just send a bunch of seeds. Usually these are like lambda bits. So this is the first variant. And the second variant is different, of course, and it exploits a different idea. So the idea is that now, instead of choosing just bits for my challenge, which leads to an error of 1/2, which means I have to repeat many times, I should try to reduce this error by having larger challenges. And so what I can do is that I can use multiple public keys and then use the challenge to just pick one among them, which is, by the way, what I'm already doing. Essentially, I have G and G prime, my public matrix and the public key, and these are just two instances, and my bit is 0 or 1, so it picks one of the two. Well, instead, what I could do is just produce, say, R different instances, where R is a certain power of 2 to the L. And then in the context of my rounds, right, in the context of my rounds, I will just choose matrices according to the bits, but I group the bits L at a time. So as you well know, L bits correspond to an integer between 0 and 2 to the L minus 1. So for each of these, I have a particular public key that I can use. So when I go to verify, I will use that public key there given by this bit string. Okay? So now each of these components of the signature points to a different public key that is used. This includes the case Q0 and G0, which are the initial one. Here's the trivial case. So with this variant, essentially, we just need to modify the security proof again slightly. Instead of using code equivalence, we use multiple codes, what we call the multiple codes linear equivalence problem, which essentially asks to find a map between any two codes among a collection. We show that this problem reduces tightly to the code equivalence problem. We have a simple probabilistic argument. We have about a loss of 1/2 in the argument, but this is not a big deal. And the advantage is that we now have multiple challenge bits. So the cheating probability of an adversary is not 1/2 anymore, but is 1/2 to the L. And therefore, we get a trade-off between a public key and signature size, right? So we get multiple public keys. So my public key is going to be bigger, but I'm going to need fewer rounds. So my signature is going to be smaller again. Why are we doing both of these things? Is because the main problem with these zero knowledge protocols was the long signature, right? And we're trying to find ways to reduce the signature size. And in fact, we can combine both of these techniques, right? This is why we call it less FM, because we have the F variant and the M variant, and we can put them together. We can modify the proofs accordingly, and we just have to choose our number of rounds in the proper way. Okay, so this actually allows for a great flexibility in designing the signature because we can push on one side or push on the other. We can make our signature really short. We can make our key really big or vice versa. Okay, we choose new parameters after what Bulens showed an improved method for solving code equivalence. So we're quite happy that, in fact, this steered some insight into looking into better solvers for code equivalence as well. And we also provide a full security analysis in the full version of this work, which is online as this ePrint report. And we are still working on the full security analysis, by the way. So in terms of performance, I have very short time, so I will just give an overview. Normally, you consider 128 classical security bits. This corresponds to about at least 64 quantum security bits, let's say for short. And here is the overview of what happens, right? So for example, if we are trying to optimize for the smallest public key possible, while keeping the signature decent size, we get less than 10 kilobytes of public key with about 15 kilobytes of signature. And we use the monomial equivalence version with the F variant. And similarly, we can try to minimize the signature. You see that our signature can get really small, 5 kilobytes, but we get a larger key. And we can try to have a balanced version, which is certainly useful in few applications. And this keeps the sum of public key and signature below a certain threshold. Yes, exactly as described here. This compares actually favorably. That's why we're excited about this work, is because when we look at other code-based signatures, we are definitely better than them in any aspect. When we compare with other non-zero knowledge-based schemes like Wave, for example, which is based on trapdoors, right? So we said before, this leads to very large public keys, about 3.2 megabytes. And so we are definitely an advantage in that sense. When we talk about other schemes, Relinde before introduced rank-based cryptography, rank metric. Right? So we have a scheme called Durandal, which has similar ballpark in terms of public key and signature size, although they are based on rank metrics, so it's something different, different kind of problem with their own drawbacks and advantages. So in the end, we have a very viable scheme with high flexibility. We can modulate the parameters. It's also the first instance of a code-based signature scheme that is not based directly on syndrome decoding, so directly on the hardness of the coding, right? We're based on the problem of finding an isometry between codes. We have provided our variants and we optimize performance greatly. And we are still working, of course, on developing this line of work with an implementation, as well as fitting in different signature functionalities like ring signatures and identity-based signatures, and completing our study of the security of the best solvers for code equivalence. So I'm a little bit late already, so I apologize for that, but I want to thank everyone again in the audience, as well as the organizers for having me. So thank you for this.